Good evening. Yes, I welcome you to our knowledge sharing. I know at the moment it's like a one-way sharing knowledge, but time will come and we shall be handling live discussion where we shall be sharing our knowledge, but for now it's okay. I'm just trying to share my experience and try to look at how best we can help, especially the younger engineers who are coming on board. I also expect you guys to, if you have anything, you can still also share your comment so that we learn. It's a two-way thing. Now, I just wanted to look at skew bridges. I know every time you are faced with a skew bridge or box culvert, there are so many questions that come to your mind. So in the introduction, a skew bridge slab is a type of bridge deck that is not perpendicular to the support system. They are used when the road or highway crosses a waterway or another road at an angle. The design of skew bridge slab requires careful consideration of the structural behavior and load distribution. Definitely you will see the load pattern as we go down. It's not straightforward like bridges that are at right angle or orthogonal or square or rectangle. So when you look at figure 1, in early days there were no skew bridges, and so engineers would do, when you are approaching the bridge, you have to first go like you are bypassing the point and you turn at an angle because of this philosophy where they're saying normally when you're approaching a bridge, you should approach a bridge straight so that you are able to see where you're going, because the bridge has that emotional attachment when you're crossing, and so normally the vehicle should be aligned to the carriageway on the bridge from a distance, so when you are coming you are able to navigate and get out of the river. So you can actually look at Karuma down, it's actually the same figure 1. So now in 1960s when they were putting this bridge, if the technology of handling skew bridges were already there, then definitely from that point there and this point, that's where the bridge would have been, or from this point coming this somewhere here. But because they didn't have it, so they had to do it this way here. So you find it's a bit unique, it's a bit difficult, because if you lose control in this area, and this area, it is very difficult to get back on the bridge. You will find yourself in water, and that is the side on coming from Noya side. So you find the Noya side is here. So this side, when you're going, that is the Kampala side, this is the Gulu side. And normally trucks lose control here and get in here and get dragged under the bridge and don't get these trucks here. It's very difficult to get the trucks. So the issue of turning at this point when you're also sloping is not the best. So these were the challenges faced by the early engineers in the 18th, 19th centuries. But at least today in the 21st century, I think skew bridges have now dominated because there are softwares. People have developed ways of designing, analyzing, loading and analyzing, looking at the load distribution. So if you look at figure 1 here, so you would come and turn at 90, and so it is like a recessed curve, an S curve kind of. So that means you need to super elevate. If it is very close, like the Karuma is super elevated on either side with a small straight here. So this, but if you have good turning, You can turn maybe 100 meters far or even 50 meters away, and you put your vehicle straight. Even here, get out at also off by another 50. So in a way, you are able to. That is when you have enough land, and then the terrain is favorable. So basically, that was figure 1. And really, if you look at this, there were no skew bridges in the early years, and so people are all engineers. Even personally, when I started designing bridges in 2005, 6, this is what we used to do, not the skew, until I joined Surrey University. That's when we, in the deck loading and analysis, that's when we learn and discover that skew bridges can actually be designed. You can actually analyze it, model it, analyze it, and design. Now, another scenario, number 2, is you find it has its own, you keep the bridge straight, at right angle to the axis, or the inlet, outlet, or approaches from either side, not in and outlet. That is applied for canvas. So as you approach here, you pull the abutment further. Even that said, you pull, so you find this part of the abutment into the embankment or river bank. This side tend to be encroaching into the river flow area, and if you don't handle it very well, you will find the scoring starting at this point and also affecting here. And once the scoring is happening, it will undermine the stability of foundation, and before you know it, there is going to be differential settlement and tilt. So the bridge will be tilting towards here and there, and it will cause a bit of twisting, and that in a way will definitely cause a bit of isolation and stability concern, and the bridge can get out of plumb and also eventually collapsing. So this one, if this was 20 meter span, you will almost put 40 meters here. You make it straight, but since it's skew, the skew length will be too much because you are trying to get away from the river bank to safely site your abutment. So definitely it's going to be, the cost will be twice. You get it? So that is something you need to know. Then scenario 3 is now when skew bridges were discovered. That is when you just come at is get to know the skew, the skew angle, and then orientation, and you go straight without a problem, and then you design. So the abutment, the pier support system will all be aligned to the floor. You get it, will be aligned to the floor, and then you have your skew angle taken care of in your design. Of course, there's an equal distribution of forces, but still that will be taken care of. So here now in number 1, there were no skew bridges in early years, so that's one you need to know. And when you look at this figure 1, 2, 3, we'll also elaborate on that. So you get to know, but at least no big worry today. You are able to do that. And also there were interruption in road alignment on the either approaches. Use of S-curve as seen in figure 1. So because there were no skew bridges, there was a lot of maneuverability way of how do you access the bridge, and that would ask for more land, very tight curve, expensive construction, and so forth. So that one is you need. And secondly, the same in number 2. So for item for number 3, maintaining alignment straight but with longer and expensive bridge, including use of middle pier, but foundation could be affected by score. I've already explained. So you have to, because if this was 20, you end up doubling almost to 40 or 45 here. Then because it's longer, you need now to support. So additional sound foundation definitely cost is going up, though the cost of deck system will be lower, but the foundation will be expensive. And remember, if you can't put the pier support perpendicular to the road, it has to be skew and aligned to river. So definitely it's also going to be what? Also going to be longer. Everything becomes complicated. So those are some of the hazards or difficulties and challenges faced by our designers in the early years. But at least today we are not doing so much badly, because you have softwares, you have there are manuals, there are codes, there are literature that we refer to. Later, after discovery of skew bridges, figure 3 became common in the modern days design and construction. However, there are points worth noting. Definitely, we are going to look at it. So when you look at Karuma Bridge in northern Uganda, linking south and north across River Nile, downstream of Karuma hydropower dam, just newly constructed, you find that these were the old days. These were designed and constructed in 1961, 62, 63. So definitely now, when you look at it, it's outdated. The new one is going to be going straight above here without this. This one now is an outdated design, because right now we have capacity to do proper siting, proper modeling, proper loading, and then analyzing. So that is something that we need to take note of. Of course, there are varying key design considerations, skew angle. So normally we have the angle between the bridge deck and the support affects the structural behavior and load distribution. So the different angles have different load response or action effect on the bridge. Where if the skew angle is within 15 degrees, normally you treat it like a normal square or rectangular or 90-degree deck slab, because it has most of the distribution of load tend to be not too much. But anything that is going more than that to 25, 30, when you design, you are going to find quite a big shift. So it is very important. Now you see from the literature, live loads complicate the situation since they can be a significant proportion of the total load. It is sufficient for the purposes of analysis and design to investigate the moments at a new critical points and reinforce according. So reinforcement also has to go according to the angle. So if your angle is the skew angle is within 15 degrees, you may reinforce normally like a normal. But as soon as the angle started changing, then there's what we call aspect ratio. So when you look at those aspect ratio, we shall look at it later, you see, it will help you to understand how to align your reinforcement and also detail it. And also one thing you need to know here is that because of this skewness, this obtuse angle here tend to have was this obtuse, this angle which is more than 90, they tend to experience more loads than the acute angles. Even the reaction change. Actually, you needed to also take note here before we go far. These turning points you see here, where you have the turning, this point and this point, the reaction tend to be more than on this side and that side. And that is why for Karuma, if you look at it, when we had the vibration on this side, it was the upstream side here, because there are two bearing support here. So the one at because of centrifugal force here and the skew tendency, because the vehicle comes as it is turning, still you have that outward force being exerted. The outer tires tend to exert more force than the inner one, and because of that, the bridge tend to lift towards the upstream, but because it is fixed, so that is the imbalanced forces tend to get distributed. So the bearings which are here and this side tend to experience excessive force than these on the inner side. The outer radius tend to experience more force than the inner radius. The same applies to this side, and that's why we realize that even the anchor balls were all bent and there were gaps between the bearings and the sole plate, and that is the bottom flange. So definitely that means that even in design, and whoever is trying to model need to understand the properties of the bearing. There are different bearings you have. You may find that there are special bearing that you need. You may not have elastomeric bearing in in either of this area, or you need to know if you have to do elastomeric bearing, but there could be certain parameters that need to be adopted. You may not have them uniform because of the response to these abnormal forces. So it is very important. So someone can model this, and then using solid, firm, and understand. You can still do the normal plate analysis, global stuff, frame system analysis, and you will get to know the different reaction. Then that reaction you can also try to model and see what kind of bearings you can have. You will not have the same bearing here. You'll have different. So, but when you model now and with your frame, if you are an academician, you can go further, and then you do a bit of research and come up with something and see how best, what kind of bearing, how do you orient the bearing, what need to be done. So that's the load distribution. Even if it is imbalanced, it's a bit receptive by the bearings and with minimal destruction. So it's very important that. So when you look here now, we realize that when you place your load at the center, this is now when you place it at B. So this is the implication. You can see the load distribution. These are the contours you can generate, and you have a look at, and then you get to see the worst case. Now when you and then the reactions, you find that these are the obtuse angle, which is here and there. You see that 13.7, 13.7. This is when you are using a 100 kilonewton in mid-span. So then you would expect to have normal distribution all, but now it is not. It is imbalanced. These one are the acute angles are almost half than the obtuse angle, and that is how. And the distribution tend to move in reducing value towards this acute. Even here towards the acute angle, but in reducing value. Now, when you try to put your load at A, then this is how the distribution happen. You can see. So it's not coming straight here. It tends to radiate, but towards the obtuse. So that's the maximum, and then moving. So this is a moment distribution due to point load near edge of the slab parallel to the bridge. So basically, this is briefly something that I wanted to share with you. I don't want to talk too much. I just wanted you to be aware. Now, what we need to know here is that the moment distribution, actually for this kind of deck system, it experiencing all this load, the tension, shear, and twisting, moment, shear, and twisting. So you are going to realize that both angles you need to take care when you are reinforcing, and all your reinforcements should be the U-type at the end, not just this simply bending of reinforcement. And then so if I was to have a shape, the U-type, I wish I would get the U-type here and I show you what we needed to do. But if not, then we could easily draw our own, and then you would still have a look at. So I cannot see that. There's nothing I can see for the U, but I would actually draw this, and then I will again draw. I'm finishing here now. This one, and then the last one would be now here. Exactly. So this is the kind of, at every corner here, there, you need to make sure you're sorry. It takes on that twisting effect, because the whole thing, I told you, we have seen the imbalances. This area tend to take more loading, but this load tend to reduce in this direction. It means there's twisting of this deck system throughout. There's moment throughout. There is shear value. So you need to take care of all this. So this is briefly about skew bridges. We shall get more time with some example and more modeling, and then we can look at it deeply. So basically, that is what I wanted to throw to you guys, and then you look more and read. With this, I say thank you.